These notes are going to focus on how to find the area of a polar region. So first we want to look at the area formula and where it comes from. So it comes from the area of a sector, and it might have been a while since you guys have learned that, and so I'm going to go ahead and kind of review all of that. So if we were to find the area of an entire circle, we would say the area is pi r squared. Okay, so that's old news. We've done that before. An area of a sector is like if you took a piece of the circle. And so what we would say is we want to find the entire area of the circle, but then we want to figure out what this portion is so we can find like a percentage of the entire circle. So we would say if this is some angle theta, then it would be theta out of 360 degrees. Or for us, we're going to do theta out of 2 pi because we know that 2 pi is equivalent to 360 degrees, and all of our derivatives have to do with radians. And so we want to make sure that we are continuing to work in radians. So if we simplify this a little bit, the pi's cancel, and we get theta over 2 times r squared, which is the same as 1/2 theta r squared. Okay, so that's basically what we're looking at as far as our area of a sector. Now, when we start talking about graphs that are changing and radiuses that are changing and derivatives and all of that, then this starts to get a little bit more complicated. So we remember from our last set of notes that dr d theta talks about that as the radius changes, the angle changes. And so that's d theta. And so what we're going to have for our area formula is 1/2 r squared d theta. So that d theta represents that changing angle, and then we have the r squared, and then we have the 1/2. And we always do this with bounds, so from alpha to beta. And so the reason we're using our bounds as Greek letters is just because we typically use a Greek letter to represent our angles. And so this reminds us that our angles are represented instead of just like x and y coordinates, okay? So if you look at this, let's say that this is the entire area, kind of like area under the curve, but here it's not really under the curve, it's like towards the center, so we're thinking about like a radius, under the radius, I guess. So the way that we're going to find the area under the curve for this is instead of breaking it up into rectangles, we're going to break it up into triangles. And you can see that all of those triangles are approximating little areas of sectors, and then we can add them together. And so that's what is meant by this integration from alpha to beta. It's just like what we did with Riemann sums, where the more triangles in this case, or the more rectangles we would get, the more accurate our approximation was, and that the integration represented infinitely many rectangles. So now the integration is going to represent infinitely many triangles, and if I have enough triangles, then my area is going to be an exact representation. Okay, so if you want to write a note to yourself about that, this is the same thing as Riemann sums, just using triangles instead of rectangles. Okay, so let's do a couple examples. These problems are why you have been memorizing if the graph is completed from 0 to pi or if the graph is completed from 0 to 2 pi. These are the problems that we needed to know that information for. So if you look at this, this is a rose graph. It has an odd number as the coefficient for theta, so that means it has an odd number of petals we can see from the picture, and so that means that this is from 0 to pi, and that's going to be important when we do the problem. Okay, so if I look at this, what I want to do is I'm going to find the area of one petal, okay? So I'm going to say area, I know that the area formula is 1/2 of alpha to beta r squared d theta. And so if I'm going to say 1/2 from 0 to pi, and then r is 3 cos 3 theta squared, so that's r squared d theta. If that would be the area of the entire picture, then I only want one petal, so I'm going to do 1/3 of that. So I'm doing this because it gives me one petal instead of 3. Sorry, that was my alarm reminding me to do my back exercises. All right, so I'm going to go ahead and continue this problem by hand just so you guys can see all those steps. Now this unit is going to be one where we will often do the problems in a calculator just to get the answer quickly. However, these are questions that are fair game to do by hand, and so every so often I will be asking you to do them completely by hand just to make sure that's not a skill that you lose. So this is 1/6 from 0 to pi. And then if I think about squaring these things, 3 cos of 3 theta multiplied by 3 cos of 3 theta would be 9 cos squared of 3 theta. And I'll go ahead and I'll move the 9 to the front. And then there's no way for me to integrate this by hand the way that it looks right now, and so I'm going to take this and use my power reducing formula. So if you guys recall, cos squared is the same as 1 plus cos 2 theta divided by 2. And so I'm going to say this is 1 plus cos, normally it's 2 theta. If this had been just a theta, it would have been 2 theta. So that means I need to double this angle, which would make it 6 theta. And I'm keeping the pi and the 0 and the 9 over. Well, I can call that 3 over 2. Okay, so if I go ahead and split this into 2 pieces, I'm going to be taking this 1/2 and moving it to the front. So 3 over 2 times 1/2 would be 3 over 4 from 0 to pi of d theta plus, and then the cos also has the 1/2, that's 1 cos over 2, so 3 over 4 from 0 to pi of cos 6 theta d theta. All right, so this one is pretty easy. I just have the 3/4. If I take the antiderivative of d theta, I just get theta, and that's going to be evaluated from 0 to pi. This one is a little more complicated because we do have u substitution. So I know a lot of us are uncomfortable completely turning the problem into u and not switching back to theta. So I'm going to use this as an opportunity to remind you guys how all of that works if we want to keep the problem in terms of u. So I'm going to say u is 6 theta. That means that du is 6 d theta. And so in the problem, I'm going to use 1/6 du equals d theta. Okay, so that part we're comfortable with. The part that we usually have a hard time with, from what I've noticed, is this part where we take the bounds and we convert them into u. So I'm going to say u of pi would be 6 times pi, so see how I'm plugging this in for theta. And then u of 0 would be 6 times 0. So when I do this problem using u substitution, my new bounds would be 0 to 6 pi. And then I have cos u du. Okay, so I'm left with 3/4 theta from 0 to pi plus. The antiderivative of cos is just sine, so I have sine u evaluated from 0 to 6 pi. So I just wanted to review that again because I've noticed you guys avoiding it. Goodness gracious, I forgot some stuff. I have the 3/4 and I also have the 1/6. I was so focused on the u substitution, I missed it. Okay. So I'm keeping that coefficient from that, and then I have this from my u substitution. So 3/4 times 1/6 would be 1/8. Okay. So as I was saying, the reason I wanted to do that is because I've noticed you guys avoiding it, and it's not hard to do, and I thought maybe if I explained it again, then it would maybe make you guys a little more comfortable. Okay, so if I evaluate this part, I'm going to have 3/4 of pi minus 0. For this part, I'm going to have 1/8 of sine 6 pi minus sine 0. So that's 3/4 pi minus 0 plus 1/8. Sine of 6 pi is the same thing as sine of 4 pi, which is the same as the sine of 2 pi, which is the same as sine of 0, which is 0, 0. Okay, so none of these equal anything. And so this is 3 pi-4ths. So that's the area of just one petal. Okay, now I think this is the easiest way to do the problem, to just find the area of all the petals and take 1/3 of it. But I want to go over a little bit more because I think it helps with conceptual understanding a little bit. Okay, so what we're going to do is I'm going to say if I didn't have a calculator and I had to completely do this by hand and I wanted to find these bounds for the petal, I'm going to go ahead and I'm going to take the equation r and I'm going to set it equal to 0. And the reason I'm going to do that is because the petal is formed by making an intersection at r equals 0. That's how the petals are formed, is you have a curve that goes in on itself and hits 0. So I'm going to say 0 equals 3 cos 3 theta. And then I'm going to go ahead and solve for this. So divide by 3, 0 equals cos of 3 theta. And then I have to think where on the unit circle is cos, or is the x-coordinate 0, and that happens in 2 places, at pi halves and 3 pi halves. So I set up 2 equations. I say 3 theta equals pi halves plus 2 pi k, and 3 theta equals 3 pi halves plus 2 pi k. All right, so I'm going to go ahead and divide by 3, 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 divide by 3. So to get all the places where this happens, I'm going to have pi sixths plus 2 pi thirds, okay? And this would be, if we have 3 pi halves divided by 3, that's just pi halves plus 2 pi thirds. Okay. All right, so that means the intersections are at pi 6. If I add 4 6 to that, I get 5 pi 6. And then I'm only going from 0 to pi, so that one's done. Pi halves plus 2/3 would be bigger than 1. Okay, so these are the 3 places where you can see those petals being formed. So, and you can see it right here. I've got pi over 6. I've got 5 pi over 6. I've got the pi over 2. Okay, now if we look at the picture to kind of make sense of it, I can see that there's some symmetry going on here. Symmetry is definitely your friend in these pictures. So this part of the petal right here is from 0 to pi 6. This part would be, I'm going to say, from negative pi 6 to 0. And that's because technically this is 11 pi 6, and I'm not going to say 11 pi 6 to 2 pi plus 0 to pi 6. That's just kind of obnoxious. So if I wanted to find the area of only this petal, I would say I could do this formula, and I could make my lower bound negative pi 6 and my upper bound positive pi 6. If I wanted to find the area of just this petal, my lower bound could be pi halves, my upper bound could be 5 pi halves. Using some symmetry here, if this is, I meant 5 pi 6. Using some symmetry here, if this is 5 pi 6, I know this is 7 pi 6 and 3 pi halves for the other petal. Then if I wanted to find just that petal, I could do 7 pi 6 to 3 pi halves. And if you plug all of those into a calculator and check the decimals, they're all the same. So, like I said, I wanted to show you kind of conceptually what's going on here, but clearly this would have taken some extra work that's unnecessary because we can just find the entire thing and divide it by 3, basically, or multiply that 1/3, the 1/3 in the front. Okay, so just kind of keep that in mind. All right, next we have a limacon. Limacon? I don't remember. We looked it up, but I can't remember how it's pronounced. With an inner loop, and so we know these are 0 to 2 pi. And so what I'm going to do is I'm going to set this equal to 0 again, and the reason for that is because I want to figure out what the numbers are of the theta that makes that inner loop to start being formed. So I want to see where this curve starts. I know it's going to start at 0, so I want to see what theta value makes the start of that inner loop and what finishes the inner loop. I just want to know what those numbers are, okay? And since that inner loop happens at 0 and it's crossing over on itself, that's why I'm going to set it equal to 0. So 0 equals 1 minus 2 sine theta. I'm going to go ahead and minus the 1 over. And divide the negative 2 over. And now because my interval is from 0 to 2 pi, I'm just going to picture where on the unit circle we have a y-coordinate of 1/2. And so that happens at pi 6 and 5 pi 6. And now I'm going to go ahead and show you something on the calculator. Okay, so I'm going to go ahead and put my calculator into polar. I'm going to change my window, so I like the 0 to 2 pi like this. What I'm going to do is I'm going to make my step even smaller just so that you guys can see it graph a lot more slowly. So if I do like pi over 100, it's going to graph it way more slowly. I can see that if I want to be able to see the screen really well, that maybe negative 10 to 10 is a little bit too zoomed out. So I'm going to do negative 3 to 3. Okay, and then if you graph this, you can see... Oh, I didn't plug anything in. I was so confused, you guys. There we go. Okay, type the equation in, that's important. So if we graph this, so I went ahead, I hit enter, which paused it. So you can see that the graph started right here, and then it did this little part, and then it did the loop, and then it did this little part, and now it's going to continue doing the rest of the circle, or the line Makan, whatever the shape is, okay? So I know that it goes from 0 to 2 pi, that's how we graph the entire shape. What I'm going to do is I'm going to switch it. I still want to have an interval that is a length of 2 pi, but I'm going to switch it so it starts here, and you'll see why in a second. So if I take this and I add 2 pi to it, then I'm going to get 13 pi over 6. And the reason I'm doing that is because I still want to have an interval of 2 pi. I just want to start it in a place other than 0. And so here I'm going to show you why I did that. So for my window, I'm going to change it to pi 6 to 13 pi 6, like this, and graph it. And now you can see the reason I did that is because I made it so that it would graph the inner loop first, and then it's going to graph the outer loop. And because I made it so my new interval is still an amount of 2 pi, it still graphs the whole thing. So if you look at this, you can kind of tell which one's the inner loop and which one's the outer loop because this interval is smaller, this interval is bigger. Okay? So on our paper, we're going to go ahead and write that pi over 6 to 5 pi over 6 is the inner loop. 5 pi over 6 to 13 pi over 6 is the outer loop, all right? And so for us to find the area between the loops, we're going to do the outer loop minus the inner loop. So I'm going to write that over here, that the area is the outer loop minus the inner loop. Okay, so I'm going to go ahead and use my formula. I have 1/2. My bounds for the outer loop are 5 pi over 6 to 13 pi over 6 of r squared minus the inner loop and then you can plug that in all at once or you can plug it in as 2 pieces. But when you plug this into your calculator, you get 8.338. And if you have a calculator at home, I would encourage you to practice plugging that in just because it's a lot of parentheses. And so it's good to make sure that you're able to do that correctly. Okay, let's go ahead and look at the next example. This one, that's so dark. This one, I was trying to get a good picture of it. It looks better in color, but they didn't have like the nice little pre-printed images for me. So here we're going to do the same thing. We're going to find the area of just the inner loop this time. And so again, you can see that the loop crosses at 0. Maybe I'll trace this. That seems to be easier to see. Yeah. we go. I can kind of see it. Ish. Okay. So I'm going to say 0 equals 2 minus 4 cos theta. I'll subtract the 2 over. I'll divide the negative 4 over, and so negative 2 divided by negative 4 is positive 1/2. And so I'm thinking, because I know that this has an interval from 0 to 2 pi, I'm thinking where on the unit circle is there an x-coordinate of 1/2, and that happens twice. It happens at pi thirds and 5 pi thirds. So I'm going to say pi thirds and 5 pi thirds. And so just like the previous problem, we're going to manipulate this graph, and instead of starting it at 0, we're going to start it at pi thirds. But we still want it to have a length of 2 pi, or an interval that is an amount of 2 pi. So pi thirds plus 2 pi is 7 pi thirds. Okay, and what I'm going to do is show this to you on the calculator so we can kind of prove that it's doing what we wanted. So 2 minus 4 cos theta, I'm going to start off doing 0 to 2 pi so you guys can see that. I do need to change the x values here. This goes to negative 7. And this goes to 2, and then this way I did negative 5 and 5. I don't expect you to be able to see that very well, I just am remembering what I did. Okay, so if I graph it, you can see it did half of the inner loop and then the picture, and now it's going to the other half. So we want to manipulate this problem so that instead of doing half of the inner loop and half of the outer loop, we kind of start it in a good spot. So if I switch it to start with pi thirds, and to go until 7 pi thirds, you can see it's starting on the outer loop and it's doing the entire outer loop, and then it finishes on the inner loop. And you can tell here because this is a bigger amount, this is a smaller amount, so outer loop, inner loop. Okay, and we're going to go ahead and write that down. Pi thirds, 5 pi thirds is the outer loop. 5 pi thirds, 7 pi thirds is the inner loop. And so to find the area for this, we're going to do 1/2, 5 pi thirds to 7 pi thirds of 2 minus 4 cos theta squared d theta. Again, I'd encourage you to plug it in yourself. It's 2.174. Okay. What I did here over on my notes is I was like trying to go ahead and do it by hand, and I ended up getting to use substitution and feeling done with it. So I might do it again, but on a piece of paper where I have more space. But as you can see, it's beneficial to practice these by hand because they do get pretty convoluted, and so we want to make sure that we can still work with those problems when they look like that. Okay, so next it says find the points of intersection between the line Makan and the circle r equals 1. And so I'm going to go ahead and graph this so you guys can see what it looks like as we graph it. So 1 minus 2 cos theta, r equals 1. I'm going to go back to 0 to 2 pi, not 2e, 2 pi. And then this is 1, so I'll go ahead and I'll make my window go from -3 to 2, and then -2 to 2. Okay, so you can see it. All right, now it's going to start graphing the circle after this. I paused it. I want you guys to see as it graphs the circle, so it intersects right here, so we're going to find that point. This is not really an intersection. If you notice, it's coming up alongside the loop. It's going to touch the loop. We can see that in the picture, but it's not crossing over. It's just coming up alongside it, so we're not going to call that an intersection. And then it intersects it again when it makes the circle. So when we look at this, we're going to say this is not an intersection. It's just alongside. So when we solve it, we're not going to find an answer there, but we are going to find one here and here. And you can actually tell what the intersections are just by looking at the picture, but we're going to go ahead and do it by hand anyway. So if r equals 1 and I want to find the intersection, then I'm going to take this 1 and plug it in for r. So I'll minus the 1 over, and I'll divide by -2. And now I'm going to think about where on the unit circle, and I'm thinking the unit circle because I know this has an interval from 0 to 2 pi. So where on the unit circle is there an x-coordinate of 0, and that happens in 2 spots. That's at pi halves and 3 pi halves. And I already knew the r value was 1, so the point is r value of 1, theta value of pi halves, r value of 1, theta value of 3 pi halves. And you can tell just by looking at the picture that's what it was, but they won't always be quite that nice.